Good morning, and welcome to our presentation on equitable access to scarce NGSO resources. I'm Mark Dankberg, Chairman and CEO of Viasat. The main topic here, we're going to talk about the need for new regulations to preserve everyone's access to space in the presence of mega constellations that will have thousands or tens of thousands of satellites. This affect pretty much anybody that's in the satellite industry or even just users of satellite services. Everybody should be paying attention to these issues. We're going to start with the space debris issue, which is a growing concern for multiple reasons in terms of just access to space and or the ability to use these low Earth orbits economically. But it's not just space debris. We're going to talk about two very interrelated issues. One is the large numbers of unreliable satellites that threaten orbital safety for LEO that can result because of these mega constellations, and also that the mega constellations could completely preempt all spectrum in LEO or NGSO orbits and basically make it impossible to launch additional constellations in the future. Unfortunately, the FCC has recognized the need to avoid creating new space debris. Near the end of 2018, the FCC issued a notice of proposed rulemaking for mitigation of orbital debris in the new space age, and they cited that the large growth in tracked objects in space, and then also the large contribution to those objects that were due to accidental collisions in 2007 and 2009 that accounted at the time for over 25% of all cataloged on-orbit space objects. And that issue of collisions contributing to on-orbit debris is definitely illustrated by this recent European Space Agency report on space debris. In the lower left-hand corner, you can see that the arrow points to those two collisions in 2007 and 2009, and the debris fragments that were introduced into low Earth orbit as a result of that. The green color here shows that they were satellite payload fragments. This upper right corner shows the growth in satellite payload fragments that were driven by just these two events in that time frame. So you can see that the effect the FCC was talking about. And then the red here is all fragments of low Earth orbit. And you can see that's really dominated by those payload fragments. And then also you can see that not only was there these step changes, but now that there's propagation effects that are happening where fragments are colliding with each other and creating more fragments. And I'll illustrate that in more detail later. And the situation is anticipated to get far worse. These charts are from a report from Analytical Graphics, which provides space debris tracking services. And the report was done in early 2020, and it cites a representative list, not even a fully complete list of all the LEO satellites that are proposed over the next decade, shows a picture of what the world could look like surrounded by those LEO satellites. And then this chart here shows altitude for each of the constellations, the orbital inclination. The temperature chart shows how the color codes here illustrate how many satellites there are. And it definitely illustrates that there will be a lot of congestion in the very low LEO Earth orbits of around 550 to 600 kilometers, where both Starlink and the Amazon Kuiper system will go. It also helps illustrate that some of these orbits are proposed to overlap and that they will interleave or cross each other because all the different inclinations at these same altitudes. Then the report goes on to show what the collision probabilities could be for all these satellites. And the red box here shows all the different shells of the Starlink constellation. So Starlink represents less than 2% of all of the proposed constellations, but by satellite count, it's about 2/3 of all the satellites. And based on the analytical graphic models would represent about 92% of all the projected collisions, and about with objects of 10 centimeters or greater, and about 95% of all the potential collisions with objects 2 centimeters or greater. So much higher proportion of collision risk than the constellations itself, or even the number of satellites. And all those interactions exclude potential interactions that could happen amongst SpaceX or Starlink spacecraft themselves if any of those satellites were to be failed and not to be controllable. This slide illustrates what the risks are of collisions at even at these low altitudes. What this scatter plot shows is where the debris went from the 2009 Cosmos to an Iridium collision, where it scattered from the collision altitude of just under 800 kilometers up to 1600, down to 400, and the resulting fragments will deorbit far more slowly than a failed satellite would from those altitudes because of the reduced drag due to those to the smaller size of those objects, and they could last for decades or even a century. This chart is also from the Analytical Graphics report, and it compares the estimated collisions that occurred in 2019, given the orbital situation then, compared to what it would be 10 years out, including the cataloged objects that were used in the other analysis. You can see in 2019, the dominant effects were debris colliding with itself. That's the gray stuff, and that's the really artifacts of those two collisions that we've noted before, and also debris interacting with active satellites. Whereas at 10 years out, you can see that the dominant altitude of estimated collisions would be in that very low altitude of the mega constellations and its satellites interacting with each other, or to some extent with debris, and that the risk at those altitudes is 250 times greater than it was estimated in 2019. And note that the scales change substantially between the two charts. So one of the points we're going to make multiple times here is that satellites that fail can't avoid collisions. This is an example of what happens when the satellites fail. This is a Starlink satellite that was launched in 2019. These two plots are from Jonathan McDowell. They have the same timeline. This one on the right is zoomed in, and you can see that the satellite exhibited anomalous behavior shortly after launch and failed and began passively deorbiting. But this shows that it's only deorbited about 2 kilometers in about the 6-month time frame. So it will be in space for probably 3 to 4 years as an uncontrollable large object that can create new debris. So one of the main questions then is, what is the Starlink failure rate? And here are 2 assessments that are similar to our own analysis, one from Jonathan McDowell and one from Elias Eckley. And you can see that they're estimating around 9 to 10% of the satellites have either deorbited, already re-entered, or are not maneuvering and failed. And that's for satellites that are essentially only been in orbit for generally less than a year out of a projected 5-year life. So that's quite alarming. This slide compares the first Starlink launch, which had 60 satellites, to the first 3 launches of 74 OneWeb satellites. And you can see in the first Starlink launch, a large number of them have already been deorbited, and some have re-entered, but there's a bunch that are still in the process of passively deorbiting because of the control systems having failed. And you can see here's the OneWeb satellites, where all of those satellites have either reached their nominal operating altitude or in the process of orbit raising, and none appear to be failed or to have re-entered. And this illustrates one of the points that the FCC was concerned about in their NPRM in 2018, which is that satellite operators may take advantage of the fact that they can tolerate high failure rates as opposed to preventing high failure rates. That is, that satellite operators may not be suitably motivated with current regulations to launch highly reliable satellites that don't create collision risk. And in fact, in a Starlink engineer Ask Me Anything session on Reddit, that's exactly what a Starlink engineer pointed out, which is that they do have some redundancy on their vehicles where it's easy, but they primarily trust in system level fault tolerance so that they can just launch more satellites. That's their core competency, and they can tolerate failures. So now the FCC has proposed an aggregate collision metric, which is under consideration and which can deal with this issue. The aggregate collision metric integrates the NASA debris assessment software, flux collision probability model with the reliability of individual satellites, and it effectively limits uncontrollable satellites that cannot avoid collisions. It's light touch regulation. It doesn't preclude launching a large constellation. It just says that if you have a large constellation, you need a high reliability. And it enables operators to make trade-offs of constellation size, the bandwidth or functionality of each spacecraft life, the reliability of each, and the amount of redundancy they use to achieve that. The actual in-orbit reliability is readily observable, so it doesn't add a lot of regulatory oversight to see if applicants are complying. And you can use a statistical reliability analysis of the on-orbit satellites to predict what the failure rates will be for the entire constellation, and then preempt launching satellites that will have an excessively high failure rate. It does create an incentive for fewer, more reliable, more capable satellites, but doesn't force you to do that, and it avoids the tragedy of the commons. Notably, though, even this estimate of 0.001 is understating the actual collision risk with several optimistic assumptions. This slide illustrates the effect of the aggregate collision metric compared to per satellite collision metric. So on the left-hand side of the table, you can see that the probability or expected number of collisions under the current 1 per 1,000 per satellite standard would be an annual expected number of collisions of single digits, even with low thousands of satellites, up to 10 per year, 50,000 satellites. Whereas if you go to a 0.001 per constellation, then irrespective of the constellation size, you'd only expect a 1 in 1,000 chance of a collision over the license term for each constellation. And that results in a sliding scale for the reliability that's required for each of those satellites, where a modest level of reliability for very small constellations, up to maybe 99.5% for once you get in the 1,000 range, or 99.99% for 50,000. Another way to look at this is what's the mean time between collisions across all the constellations. And what you can see what this does is it, instead of having a mean time per collision for a very large constellation of weeks or months, it says that the mean time between collisions per constellation would be once in 15,000 years. Now, when you take into account that we could anticipate hundreds of constellations, you'll get into an expected collision probability of once per, say, a small number of decades, which would be more consistent with space safety. And then this chart will look at that analytical graphics analysis again, where with the same parameters, if you use a aggregate collision risk of 0.001 per constellation, you can see now the SpaceX system, you have less than 2% of the constellations, still a very large fraction of the satellites, which do present a higher collision risk, but they would have to control those satellites efficiently, reliably, to reduce their aggregate metric to be the same as any other constellation. So that's a way to deal with the collision or orbital safety aspect, but we still have the spectrum access issue. So let's take a look at that, and we'll show that this applies to KU, KA, and V band, because there are filings in all of those bands. So what we've done here is shown a polar plot, which shows if you look up into the sky from 33 degrees north latitude and look in a 360-degree circle with a constellation of 1,500 satellites, that's similar to the first tranche of Starlink shells. Here's what you would see within about a 40-degree elevation angle and about a 25-degree elevation angle on this line. You can see about 4 satellites in view at 40 degrees of elevation, and maybe get to about a dozen, right around a dozen on the verge of that at the 25-degree elevation angle. And now if I want to find sight lines for other constellations, I can find some. They're a little bit hard to do, but it's possible, at least, certainly with 40-degree look angle, maybe with 25. But even with 4,400 satellites, you can see that essentially every angle from this point is blocked. That is, that there'd be an inline event with some satellite in within the 40 or 25-degree elevation angles of this constellation. So if that has priority over all the others, they're essentially shut out. And you can see what the situation looks like when you get tens of thousands of satellites. Obviously, it's completely hopeless. So one argument would be, rather than giving priority based just on filing order, that you'd give priority based on what the impact would be to these constellations. And this is just one approach. But if you think of it as, let's say that somebody launched a constellation with 400 satellites and that has lower filing priority, but it's only 1% of the satellites of this 42,000 satellite mega constellation. Well, if every one of those 400 were given priority over the 42,000 in the mega constellation, it would result in about a 1% hit to the aggregate capacity of that mega constellation. And then what you could do is you could say, well, what I'll do is I'll also do a 1% hit to the 400 smaller constellations. So you basically say, okay, 99% of those have priority. And now with that construct, each constellation would be affected by about 1% of its aggregate bandwidth, which, you know, given the large size of this constellation, it's easy to deal with because of that redundancy effect. So that's an example of a way to deal with it rather than just giving priority based on filing dates. So one of the questions is there some benefit to these mega constellations? Should regulatory policy really incentivize people to launch very large constellations? Are they somehow better or more efficient than smaller constellations? So we're going to examine that. And the way we did that is we took some geographic information databases, which break populations and households down into very small grids. And so we're looking at close to 10 million hexagonal cells around the world. And what we're going to look at is match that up against the orbital trajectories that were filed for the mega constellations. And remember that having a spacecraft someplace is really just like a tower. It's a place to put the satellite payload, which is really what the network access is. But that payload can only serve demand that's in view of that satellite or tower. So this slide shows the integration of the demand model along with the supply of where the satellites are. And it shows about 32,000 satellites, Starlink satellites, and about 20 orbital shells. And you can see that the vast majority of those satellites see very little demand. The demand is indicated by the bright spots on the ground, with the brightest spots and the highest peaks being where there is the most demand, remembering that about 50% of the people in the world live on 1% of the land, and about 95% of the people in the world live on 5% of the land, and land is only about 22% of the surface of the Earth. So it's not surprising that this is not a very efficient way to match supply and demand. And this shows Starlink utilization if what you do is you start assigning the demand to the satellites that are in view based on the look angles that are shown in the filings. And in this view, which shows each third of the world, the red satellites are fully occupied. The blue ones are essentially unused, and there's some green and yellow spots in here of partially used satellites. And you can see that, again, the utilization is very small because the satellites are at very low altitude. They have small field of view, and obviously most of them are over places where there's no demand at all. And you can contrast this with smaller constellations such as Oneweb, which has about 700 satellites at higher altitudes. So they have a larger field of view, and the satellites that they do have over these areas are not saturated just by the demand in small areas. So more of the satellites, close to 20% of them, would actually could be fully utilized. And Morgan Stanley put out a report this summer, which basically looks at the cost efficiency of these mega constellations, especially Starlink. And what they found is that they're not very cost effective. That is, in terms of producing useful bandwidth per capital dollar invested. And this chart shows cost per gigabit per month, so the lower the better. This is the SpaceX constellation with different assessments of cost and utility. They're estimating that only 5% of the bandwidth would actually be sellable. That's better than a HTS-KU constellation, but it's actually only comparable to what Viasat 2 was when we launched that about 2 years ago, and not as good, as good as a Viasat 3 constellation would be. And a Viasat 4 would be about 10 times better than even the best estimate for SpaceX. So we think there are better ways to scale. And here's an example of what we did with our own LEO filing, where instead of having very large numbers of low reliability satellites, we designed a system that has very high capacity per satellite, about 10 to 20 times what we think the capacity of SpaceX Starlink satellites might be, and we can have fewer and more reliable satellites. And this is an example of how that might play out. Whereas a constellation of about 4,400 Starlink satellites might have useful bandwidth of about 1,320 gigabits in the aggregate. A constellation of 288 satellites with 100 gigabits each at a higher altitude could have a higher efficiency and could generate over 4 times the amount of bandwidth that's useful. So if you think about, is there a public benefit to having large numbers of satellites? We think it's kind of the opposite, that the public benefit of fewer, more capable satellites. You can readily meet the aggregate collision metric because you have a much smaller number of satellites. You can deliver multiples of the useful bandwidth. You can have far, far fewer conjunction events, so that requires fewer maneuvers and fewer maneuvers for other systems that are in your orbital neighborhood. And you can occupy far fewer orbits, making more available for other systems, so it's a lot more competitive. And it occupies far fewer Earth to space lines of sight, so it's far more spectrum would be available for other systems as well. So we think this illustrates that mega constellations inefficiently consume disproportionately more orbital resources, whether it's collision risk or spectrum or conjunctions, that scaling up with more satellites is not necessarily in the public interest, and that policies should promote accomplishing missions with the fewest satellites that are needed, as opposed to coming up with the most that you could possibly put up. And this is a global problem. So the initial mega constellation failure rates are about 100 times higher than the FCC's target for those constellation sizes. Remembering, failed satellites can't avoid collisions. And it would create a race to the bottom. Whereas if you're in an orbital neighborhood and somebody else has very low reliability satellites, that disincentivizes you to put up reliable satellites because yours are at risk from the collisions from the unreliable ones. We think spectrum priority should anticipate further innovation by new entrants and avoid rewarding excessive satellites by allowing them to preempt spectrum just because of filing priority. And we think that this could benefit from advocacy for a comparable regulation for international administrations. For instance, they can do similarly to what the FCC is proposing, that is to limit landing rights and make them dependent on both space safety and spectrum equity. And this would avoid the tragedy of the commons. We think satellite broadband is responding to the market, that people are looking at these issues, and that there's no need to accept imprudent space collision risks just to advance global broadband. And that safe use of space for hundreds of innovative NGSO constellations is achievable, and that simple and effective policies will stimulate and reward the investment needed in these truly scalable, low-cost, reliable technologies and business models. Obviously, Viasat's been very active in this area, and if you'd like more information on any of this data or how to participate, you can contact either of these two people shown on this chart, who are our leads in this regulatory policy area. So thanks for listening. We'd be happy to take questions at this point.
So a fascinating presentation from Mark there on what the future might potentially hold for NGSO and mega constellation deployments, and it definitely seems that there's a risk of it getting pretty busy up there. So I'm delighted now that Mark is going to be joining us live. So I'd like to welcome Mark to the stage. Welcome, Mark. So thank you so much for joining us. We do have now some time for questions for Mark. So if you have any questions at all for Mark, then please do post those using the chat feature on the right-hand side of your screen, and we will then put some of those to Mark now. And I'm glad to say that we have some questions coming through already, so we'll get kicked off with those straight away. So, so Mark, first of all, we have a question from Andy Hudson, who asks about how we should be balancing national regulation, which is quicker to implement, with regional or global regulation, which is often slower to get agreement, and how we should balance those, as I said, when we're talking about space. So any thoughts on that at all?
Okay, good. So yeah, this brings up a really important point, which is, there's a game theoretic element to this. When you think of economics and market economics, everybody just does what's best for themselves, and hopefully that's best for everybody else. But in game theory situations, you end up with situations where you really have to cooperate in some way. And so in this particular situation, it's even more complicated because we already have a fairly critical situation in orbital debris that exists, and new satellites are being launched at a very rapid rate. So we need to move fast. What we do think is international cooperation is going to be required, but that probably the administrations that need to respond first are the ones that are sanctioning or licensing the rapid orbital rates. So that would be the US and UK as an example. And I can tell you, one of the issues in the US is that there are people in the US who feel that if the US is the only one to adopt standards like this, that other nations might be at an advantage. So kind of what we think is it probably makes sense for the US to act first, but we think that it's important for there to be a discussion of multiple nations, and that other nations follow the US lead as possible, probably on an individual basis, and then bring us to the ITU, which is probably going to be very important in making this, but we should put that to complete.
Thanks, Mark. Thank you for that. And I suppose carrying on a similar theme and looking at the opportunities for looking at kind of regional or global coordination. A question has come in from Rajesh Merotora, who asks about the concept of collision matrix, and asks whether you feel that should or can become a subject of study in any of the ITUR study groups, for example, study group 4 or study group 1. And if yes, would your administration consider proposing it as a question for study in ITUR so that a report or recommendation can be drafted for administration? So any thoughts on that?
Okay, well, obviously we can't speak for the US government on this, but what we do think is that the notion that we're describing here and is being described by other people is that there's only so much risk that can be tolerated and have access to space be preserved. So think of it as a risk budget. And the questions are, well, okay, so how much debris can we tolerate? Where should we believe it will come from? And then how do we manage the growth of that debris? And I think that is certainly a valid topic for discussion. ITU could be a good forum. We'd be pleased to see the U.S. take the lead on opposing that.
Brilliant. Thank you so much. And maybe moving on a little bit to talk a bit about the practicalities and the situation regarding all these satellites that potentially are going to be launched. I mean, you've talked about the number of satellites being launched or are planned to be launched. So, I mean, maybe is there a question of what countries are able to then do to kind of make sure that the standards are maintained, I suppose, so to make sure that the satellite operators who are either flagged under their country or attempting market access are building these satellites to a safe standard?
Yeah, this is an important issue because you have a lot of countries around the world who are spacefaring countries, but are not yet launching these large LEO systems. And I'm sure one of the things that they've got to be concerned about is how do they weigh in on this when those launches aren't coming from their administration. I think one of the ways to do that would be for those countries to adopt landing right rules in their own country that would essentially say, in order to get access in these markets, you need to adhere to space safe policies. And the aggregate collision metric would be one example of that, as well as equitable spectrum priority policies. And I think the significance of that's going to depend a little bit on how important those markets are. But I think that if enough countries do the same thing, that will certainly disincentivize operators from launching very large numbers of satellites that won't be able to get access in these markets. And again, I'm just going to emphasize the game theory aspect of this. It requires cooperation. And this is a way that I think any country can start initiating some amount of cooperation.
That sounds great. I mean, I guess, though, that there's obviously quite significant costs involved if we're looking to build to specific standards in that way. I mean, is there a concern that those costs may potentially be too high to build to these standards that you're suggesting?
Well, so it's also an important question, but I think if you think about space pollution as this, which is what this is, right? Is essentially polluting a resource, and unlike Earth situations where you could do some cleanup on a river or a lake or a toxic waste site, cleaning up space from this orbital debris is actually not even possible at these points in time. So I think what we have to do is we have to weigh the costs of not doing anything versus the cost of doing them. And what we think is actually the cost of doing things are quite manageable. Just in the example that we gave, which is a smaller constellation of much more capable satellites, I actually think that's going to be far more cost effective than the opposite, which is a very large constellation of unreliable satellites. Perfect, Mark.
Thank you. And actually, we have another question that has come in that is asking, are NGSO systems from other countries going to have trouble accessing spectrum if a 40,000 satellite US system is launched? Any thoughts on that?
Yes, absolutely. I think that's one of the game theory and cooperative issues that we need to address here, which is that, as we showed, is that once you get many thousands of satellites in space using spectrum, that there's none available, not only for other communications systems, but for Earth sensing, for scientific missions, or others as well, where the mega constellation can serve priority. And this one, in some sense, is also very critical because while there's certainly lots of demand in sovereign countries, there's also going to be demand over things like oceans, where this would just could be a free-for-all if there's no cooperation to regulate spectrum access.
And I suppose that given a lot of these systems are already being deployed, I mean, is it too late to do something, do you think, or is there still a chance to do that?
No, we don't think it's too late at all. Number one is, if you look at, for instance, the UK's space agency policies, they're already imposing standards in terms of reliability. That's one of the things on Oneweb sites in terms of why their system's been more reliable. but also the FCC, which is the administration that's licensing the SpaceX constellation, has said multiple times that all of their licenses will be subject to these further rulemakings regarding space safety and spectrum.
Perfect. Thank you, Mark. So we have just a couple of minutes left. I don't know if there's any more questions out there. If anyone did have any other questions, then please do post those now. So it's your last chance to maybe post questions. I mean, maybe Mark, as we're coming to the end, I mean, if there was one key message that you wanted to maybe give to policymakers, you know, around the world, US and around the world, I mean, is there a key message that you want to give? I mean, I think you've done that in your presentation anyway. One key message to give out to those there.
Yeah, I think that the most obvious one is that these are complex issues. You know, what we've tried to do is cite knowledgeable third parties on space safety issues, especially, and that I think that somehow there's been some sort of presumption that scaling up to very large constellations is beneficial, and doesn't look like that's the case, especially if you look at what the collision and the orbital safety issues are. And so I think that that's really kind of the main thing, is it's worth kind of starting from first principles, looking at what is the right way to scale and make LEO available for broadband on a global basis.
Perfect, Mark. Well, look, thank you so much. And as I said, that was an absolutely fascinating presentation. And thank you so much for your time in joining us to answer those questions as well. I know that Mark mentioned a couple of email addresses for his colleagues. So I think my colleagues will post those into the chat. So if anyone does have any follow-up questions or comments for Mark or for anyone at Viasat, then you can use those email addresses to send those through to. But that said, Mark, thank you so much once again. As I said, I really enjoyed that, really interesting presentation, and thank you for your time. And yeah, that's just about it. So thank you everyone for your questions and comments as well. And yeah, that's the end of the session. Thank you.
Thanks for having us.